So welcome everyone to ICTS Colloquium, and we are very happy to have Professor Jorge Kurchan from École Normale Supérieure Paris as a speaker who is visiting us for the meeting. Professor Kurchan, of course, needs no introduction to this audience for his very influential work in various areas of non-equilibrium statistical mechanics and stochastic processes. And particularly, he would be talking about something that I'm slightly more familiar with, the quantum bounds. And so, welcome.
Thank you very much. So, what I wanted to tell you is this story, which is difficult to focalize because several elements come into it. So instead of focalizing, I decided to exaggerate the thing and explicitly emphasize the fact of different elements coming into it. So, and this by way of excuse, I'm far from being an expert of some of the things that I will mention. So, okay, many threads come together and I am making a virtue of necessity. Instead of hiding this, I am sort of overemphasizing it. So one element is black holes, which you will see how they enter this story. It's a classical theory, as you all know. Their marriage to quantum mechanics, like all general relativity, is still very tentative and very partial. And it's a conflict between quantum mechanics and gravity that is considered to be, at least at the high energy physics, a fundamental open problem. So black holes, you've also probably seen it around. They are solutions of Einstein's equation that were found very early. At the beginning, it was thought it was just a curiosity, and then slowly it became more evident that these things happened, and they do happen in the universe. And okay, these black holes, these singularities where the mass is concentrated in a point, produces, it was realized by Hawking, radiation which shines out of them. So although it's very black and it's a hole, still energy comes out and they evaporate extremely slowly. And you can define an entropy, a temperature. It's, for me, has been and still is a bit of an enormous mystery. This is the solution of a classical equation where there are no particles, no nothing, and we are defining an entropy. But probably through indirect reasonings and by analogy, these quantities have been defined. And they have a certain number of characteristics. One of the, and there are many, but the one we are emphasizing, we will like to discuss here, is the fact that they are considered to be the fastest entanglers, the fastest scramblers in the universe. And I don't know if this is probably philosophical, but there are also thought experiments in which you throw one of two entangled particles inside and then do manipulations and so on. And you construct a thought experiment such that you need that this scrambling time, the time for the particles wave function to explore everything, you need it to be very fast. So let's take this as a dogma. I cannot very much give you all the details, but it has been taken for granted that the most chaotic objects in the universe are black holes. But of course, what do I mean by most chaotic? If it's a continuous thing, yes, it could be the most chaotic. But the interesting thing is that, and this is the point where all this becomes clear, is that it was found that there is a quantum bound to chaos, for example, more concretely to the Lyapunov exponent. So now the thing becomes sharp. We want the black holes to saturate that bound. Now it's very clear, black and white, they are the most chaotic objects in the universe if, for example, the Lyapunov exponent is such and such, which is the highest bound allowed by quantum mechanics. Yes, stop me all the time.
Why the attention to the Lyapunov exponent? Like why?
No,
No,
well,
but I mean, okay. I mean, why not looking at the entanglement spreading, for example,
because it's harder, because it's easier. I personally, for example, there's a long history of trying to find bounds to viscosity and transport coefficients. As physicists, we all prefer that to Lyapunov exponents. The problem is we yet cannot find any bounds for those. So it's for lack of something better that we can do. Okay, so good. Also scramblers, defining scrambler or equilibrator from Lyapunov exponents is not a very foolproof thing because things can have a big Lyapunov and be very slow in equilibrating. Glasses obviously have a big Lyapunov. I mean, these are nonlinear interactions, and yet they take ages to thermalize. So even that is not so, okay. So we want to measure with a Lyapunov exponent, but I didn't tell you how we measure a quantum Lyapunov exponent. You know the classical one where you take a particle, a system at two nearby trajectories, and you notice that if they separate exponentially, and then you define this as a Lyapunov exponent. A slight variant of this that is a little bit more robust is to let it evolve with a Hamiltonian, give it a kick with an operator B, and then bring it back with minus the Hamiltonian, and then take any operator A and look at the difference between going and coming back. Why is this nice? Because I don't notice that I don't need to talk of trajectories. I take a variable, I evolve it a la Heisenberg if it were quantum, give a kick to the Hamiltonian, change its sign, bring it back, and I may compare these two. And this nice thing of this definition is that it works for quantum. And so you do exactly that. You have A, kick, back, A transformed, and then you look at A transformed minus A squared. It's a measure of, say, this distance, and now I'm definitely quantum. I weigh it with rho, which is the Gibbs measure, take the trace, and then I develop this, and I discover that this is the quantity that measures the Lyapunov exponent. This is simply a second order expansion, okay? And so this quantity is going to be what we are going to call this expectation. If and when this grows exponentially, I'm going to say that lambda is the Lyapunov exponent. Spoiler, spin chains don't have a Lyapunov exponent. You don't have this, so too bad. What I'm going to say does not apply to them. Okay, so this, by the way, you see I got a commutator squared, and for the classical one, I got a Poisson bracket squared, and it's natural. This is what they taught us at school, that we had to changing or substituting Poisson brackets by commutators we quantize. So it's very natural. This was done by Larkin and Ovshinnikov 60 years ago. Yes?
Is this 2 lambda t or lambda t? This, in terms of Poisson bracket naturalized, yeah.
Good. In fact, if you're going to, yes, at the 2, and also you actually should average the logarithm and not that. So it would be kind of Regni Lyapunov exponent. Yes, for people who have worked with Lyapunov exponents, they would like to see a log there, an average of a log. Nobody does so in quantum mechanics. So think of it in the same spirit as instead of doing rho log rho, you do rho squared, okay? It's a kind of Regni moment. But it still measures what, but it's not quite the typical object, yes. Okay, now, technical point that has surprisingly enough an importance, but it shouldn't be conceptually. The average of this commutator, I can do it like this, which is what I did just now, but you wouldn't be very horrified if instead I split this measure in 4 pieces, put it here and take the square. You see, classically it tends to the same thing and it seems like not unnatural. And for the same price, you can accept that I cut even more and I split it in so many pieces. I am still calculating the commutator. So I have 3 versions. No good reason to choose any of particular of those, but it's something you can swallow easily. This, if you want, is going to be the biggest technical idea in the problem. The fact that we can write it in these 3 ways. And by the way, I have no proof that in all quantum systems, that's going to be, nobody has, as far as I can tell, proof that these 3 things should give you the same thing. But we all believe it. Okay, so as I said before, yes?
But the second one is just a 2-point function square, not the same.
Well, yes, wait, the trace is outside. Sorry, the trace is outside. Here too, the trace is outside. Sorry, yes. Okay. Okay, it should have an upper limit. No, it does have an upper limit, so that if this grows in the Lyapunov way, and this one too, as I said, let's believe it, then this is what Maldacena, Shenker, and Stanford prove, actually for this second one. And you will see, not for this one. In fact, I'm not aware of any proof for this one. But for this one, you can prove the following result. So lambda, it's a Lyapunov exponent. It has dimensions of 1 over time. And this is the Planck time, temperature divided by h bar. It's the unit of time, if you want, that is natural and it's model independent that you can have. But if you want to more or less understand what it means, consider a point moving on a manifold without any potential, just moving along geodesics. If these things separate because there is a Lyapunov separation on this surface because it's curved. And let's call the length of separation when this distance goes from 1 to E, 2.71. If you compare this elongation with 1 de Broglie, thermal de Broglie length, and you say that you're comparing, you get exactly this factor, the lambda, the T, and the H bar. It's a 2-line calculation. So you can swallow this thing by saying, I'm freely moving on a surface. Yeah.
This bound is independent of the Hamiltonian?
The bound is independent of the Hamiltonian, indeed, yes.
So if I take twice the Hamiltonian or very small, very big, it doesn't matter.
Then you do a calculation and the 2 goes away, I can promise you. Because it does.
Okay.
Yeah, because I had the same question, don't ask me now, but I made myself the same question and I can assure you I was reassured. Independent of A and B is more hard. This is an act of faith, which we also do for the classical case. The idea for the classical case, at least, is that I am separating the 2 trajectories, and I could do so in many ways, and I am measuring in many projections. But my vector is expanding exponentially and turning. So the projection, you have to really have a bad luck that it's 0. That's the way I accept it in the classical case. Yes.
So it's a, yeah, the reason why it cancels out is a matter of units, because e to the power lambda t, that time. So
Yes.
lambda is inverse time. So, and this is temperature over here. So they scale the same way.
Yes. Yeah. That's the answer. Good, thanks. If you double the Hamiltonian, you are doubling the temperature, and hence the lambda compensates, and you get.
Doubling the Hamiltonian doesn't always double the temperature. No, I can take a bigger system with same temperature.
No, you could keep the temperature. In any case, oops. This calculation in the appropriate units is the bound. Okay, another thread of this argument, let me make it, you all know this, it's fluctuation dissipation, you know the idea, you have a particle in a liquid, the particle is getting velocity thanks to the impacts of the molecules of the liquid, but it is also being slowed by the liquid. This is the argument of Einstein. And so, because the noisy impact of molecules is what the correlation measures, it's the amplitude at different times of the noise you're feeling. And the response is the friction, the viscosity is the response. You push the particle and you see how it responds. You want that at the end of the day, the particle has a half kT per degree of freedom, otherwise things are not working. So you need that the noise and the friction are related. This is the intuition of Einstein, and this is what the fluctuation dissipation theorem tells you. And from here, you see that you're not going to find in equilibrium, classical or quantum, any counterexamples for this. Because if you find counterexamples for this, always respecting equilibrium, you are making a real mess with a problem of equipartition on which thermodynamic rests. So, so the point of, I had a nice picture, you can think of it this way. I have more generally a system of which I make many copies. This is a thought experiment. I couple a little bit each one of these systems to a subsystem, which I'm going to call a thermometer. And then because it's a weak coupling, this is linear response, the friction of these systems to the dynamics of the thermometer is the response function. The noise that is giving energy to this thermometer is the correlation. And in order that this thermometer grabs the right amount of energy, which is the reading that it will show you, it needs that the balance of these two things be correct. And this is the temperature. So, okay, in quantum mechanics, if the thermometer is quantum, this is made by analytic continuation, blah, blah, blah. But analytic continuation or whatever cannot fail because otherwise thermodynamics fails. Okay, so noise correlation is a correlation. This is classical. Response function is the dissipation. You're pushing and you want to know how quickly it goes when you change the force. And this is the fluctuation dissipation relation in the classical context. You all know this. Okay, and this is very general. For example, this is a magnet and you do an LC circuit. This is your thermometer. You want this LC circuit to have the appropriate energy. And you can see it gets its energy from the fluctuations of magnetization. And it dissipates with a dissipation of the out of phase susceptibility of this thing. And the same thing here. Okay, so now the quantum fluctuation dissipation. This you also know, but let me insist a bit more. The quantum fluctuation dissipation you probably all seen. It's the KMS, Kubo-Martin-Schwinger relation. It's this one here. You write it in Fourier space, and it's like this. But I'm going to write it in 2 steps. The correlation is the cosine, and I introduce this intermediate step. F, the response is the sine, parabolic sine with this F. I'm not doing anything. If I eliminate F, I get this. But the interesting thing is I want to introduce this function F. And now I can, the nice thing of this way of writing it is that the tangent is not great as a function. It has poles in different places in the complex plane. These ones are okay. And now it's very easy to write these in real time, and they read like this. So the correlation reads like this function F as a fluctuate, as a translation in the complex plane. The response is the difference. So these are a commutator and an anti-commutator. And if I can eliminate df, of course, by doing the Fourier transform and getting here, I get it's equivalent to fluctuation dissipation. That's all. The only peculiarity here, I mean, it's doing the same job as Einstein thought for the Brownian particle, but at the quantum level. Okay. Okay, so now you take this quantity C, which is a quantity you define, and it reads like that. And you take a function f, which is place the role of the f, which reads like, oops, this. So these two functions are, the point is that this is a 2-point function, this is another 2-point function, and when you develop them, you get these two functions. And now the interesting point is that these two are related by fluctuation dissipation. This C and this F, they are in this relation here. So now you have two ways of, right, you have these two things that are related through fluctuation dissipation, and now very quickly you say, okay, this is a 2-time function because this happens at one time, this happens at another time, this happens essentially all at 0 time, this happens at time t. These 2-point functions in almost every system will decay relatively fast. These, on the contrary, are, remember, version 2 and version 3 that I introduced before. Version 2 and version 3 are these two that I introduced before. So in a very simple algebraic way, I can write in half of fluctuation dissipation. This picture is intended to show you half of this fluctuation dissipation. It's showing you that these two things are related through half of fluctuation dissipation. And these black things decay fast. So if I look at long times, precisely the two versions I wanted are related via fluctuation dissipation. So I have done nothing, just an algebraic step that writes this as a correlation, and this as this f function. And apart from that, just observe the fact that I get two versions of the thing that was going to give me the Lyapunov exponent. Now we're done, because if f happens to grow exponentially, when you apply the fluctuation relation, this one, it's very easy, if this is an exponential, to see that you are catching an exponential of bh over 2, because you have e to the, this thing, e to the, and so it's very easy to show that when something f is an exponential, when you apply this operator, you just get the cosine of what is in the exponent. This is half a line. And so at the end of the day, you get that the relation between this and this is the cosine of beta h lambda, the Lyapunov exponent, divided by 2. But the problem is that these two were positive, and the cosine then has to be positive. So that's all. You need this, and this is the bound. This had been noticed in a different way by Tsuji, Sawada, and Ueda, and we did a simpler way with Laura Foin and Silvia Papalardi. So in 2 words, you have version 1, version 2, version 3 of your Lyapunov. you write them together and you notice that version 2 and version 3 are positive definite, and you notice that they are related by fluctuation dissipation. Then you assume that you have a Lyapunov exponent, then you pick up a cosine, and then the only possible thing is that that cosine is positive. That's all. So when you think of it, the two hypotheses that are really entering here, not the Hamiltonian for sure, the two things that are appearing here are the fact that you wrote version 2 and version 3 and you believe that they are telling you the same. That's one thing. And the other thing is that the fact that 2-point correlations decay very fast compared to the part where you get your Lyapunov growing. So that's all. So what do we learn from this? We learn, first of all, that there is no sophisticated physics behind. There is probably the uncertainty principle, and that's all. There is nothing special here. It only relies on the KMS relation, the fluctuation dissipation relation. And this gives you the bound, because when you simplify the 2 with the 4, it gives you the bound to the Lyapunov exponent. Okay, stop here for a second, and I start with another thread of the argument. A model of glass that became very popular and modeled our way of seeing glasses, or at least some people of us, is a kind of spin glass with random interactions and random p-spin interactions. So it's not quadratic, it needs at least 3 operators. P must be at least 3. And because this would diverge, you keep it on a sphere. This lambda is a Lagrange multiplier that is not the Lyapunov exponent. And then you can do dynamics on the sphere. You can do whatever you want. And this model, it's a model of glass, and you learn a lot of things. Take my word for it. There are no particles. There is no nothing. This is a fully connected random model. It's kind of a spin glass model. And believe me, and it took a while for people to believe it, this tells you a lot, is a toy model of a glass. Now, people who, and this is yet another thread, people who were looking at certain electronic phases, you know, a metal is something that has low excitation so that an electron can be in one of them and travel. And most of them were made of quasi-particles, so an electron is essentially a fermionic plane wave. And these are the excitations. I don't need to tell most of you what is a quasi-particle. But there are systems that are very strongly coupled and yet have a lot of low-lying excitations. And this is called a strange metal. Okay, so this is a soup of things that is very entangled, definitely no plane waves, let's say. Quasi-particles are fermionic plane waves. So nothing of that, and yet they have very low excitation. So in the last 30 years, Sachdev, Antoine Georges, and other people were trying to construct models with the same mentality of the toy model of glass, but with fermions. But again, no particles, no nothing, just a fully connected set of fermions. Now these are fermions. And they believe that this, which is not a glass, because the fermions don't allow you to make a glass, however, this strongly coupled system was going to be a model of a strange metal. So a model where excitations are not simple oscillations, let's say, they are something much more complicated. Then Kitaev had a sequence of ideas. The first one is not fundamental. It's just that instead of working with fermions like the ones we are accustomed, the calculations were easier if you did it with Majorana fermions. If you don't know what Majorana fermions are, you lose nothing. Any fermions will do here, do the same job. Kitaev was clever to choose them because they're easier in your calculation. Okay, so this model is or is not, I don't know, this is solid state physicists who are discussing, a model of a strange electron metal, which means a system that is very far from being almost free quasi-particles, very, very far, and yet has a lot of low-lying excitations. This is the important part. Okay, and then Kitaev had the idea to compute for it the value of the Lyapunov exponent that I introduced before. This is where the two ideas get intertwined. And I'm sure that he had guessed it, because otherwise he wouldn't have done the calculation. It saturates a bound. So this model that was introduced for trying to mimic a strange metal now has gained the title of a bona fide toy model of a black hole. And the very low excitations that are typical of a strange metal, which is why it was introduced, now become all the states of your black hole. The system has zero temperature entropy, and that zero temperature entropy is what you connect, let's say, to your black hole. So you see that this follows a line of argument that is very twisted, and I wanted to emphasize all these elements coming into the picture. So then once this model has gained its brevet, its patent as a possible toy model, remember that I said about the glass here that there are no particles, no nothing. Okay, this is a black hole with no space, no nothing. It's really toy. But then having this first symptom, people started looking in better detail, and you get the things other things you expect from it. Energy goes like the temperature squared. Energy like the energy squared shouldn't be that. You have zero temperature entropy and more. So for the first time, you have something that, okay, it's very toyish, very metaphorical, but you couldn't do something about it. And you will see that the something about it is very interesting. Okay, so what's the something you can do? When you try to solve this model, it's completely standard. In spin glasses, this has been known basically forever. You write an equation for your correlation, and it turns out that thanks to the mean field structure, you can write an exact equation for the correlation, which you have to solve. And if you solve that, your problem is done. This is in imaginary time. And then you find, by any method, that the correlation drops very slowly, like a power law. And here comes the nice thing, that because it drops very slowly, you feel tempted to throw away this term. And you are left with this equation. And that one you can solve. And this is exactly what people did when they wanted to solve the dynamics of this model. They wrote an equation for the correlations and then found the derivative and said, because the dynamics is slow, I will throw the time derivative. And exactly the same, Kitaev and then Maldacena, Shenker, and Stanford, when they wanted to solve this, they did the same. But now one thing happens is that the moment you throw this derivative term, you don't have only one solution as you should. You have an infinity of solutions, and that they are related with one another. And this infinity of solutions is like this. If I have a solution and I stretch the time with any function h, this other object is also a solution. But notice, this is very subtle. It wasn't there, the symmetry. It emerged from the slow dynamics. Exactly the same thing happened in 1982 when Sompolinsky and Zipelius tried to solve the spin glass dynamics. They found this, what is called a reparametrization invariance. Rather than invariance, I should say softness. It's not that it's complete, so it's only approximately as a symmetry. So this is, as you can see, a film projector. Films were bands of celluloid where photos were put on and they were rolled and you could project on a wall. And this, the symmetry we're talking about is that the film is given to us and we put it on the roll, but then the speed of time is given by the handle. By the projection is passed with a handle. And when you change reparametrization, you have the same time evolution, but now you're changing the speed at which it happens. This is the pseudo symmetry that the system acquires. It is a quasi-symmetry, like this one. This cone is not entirely flat. This is metaphorical. So you can move around here, change the reparametrization with almost no effort. And as you approach zero temperature, this becomes more and more a symmetry. Okay, another thread. You have almost a symmetry, an almost symmetry, but what do you do in life when you have almost an almost symmetry in any branch of physics? And this Congress is precisely about that. When you have an almost symmetry like translation or rotation, you try to find the sigma model or the hydrodynamics of your problem. These are the low energy modes, which are almost for free. If you shear, it's not a symmetry, but it's almost like having a translation, and it costs very little. So all these quasi-symmetries you encode in something, throw away all the rest, and this is your hydrodynamics, which is nothing but a sigma model, an enriched sigma model with all your K modes. This is the standard strategy in physics, but now you want to do the same for this. I mean, the reparametrizations we know are almost for free, so why don't we write a theory for how much a reparametrization of time costs me? So the operator of this filming projection machine has a stipulated speed, but if he wants to make it a bit slower or a bit faster, he can, and he pays a little price. The price is very little, and as the temperature of the system is closer to zero, it's even more small. And now we want to make a theory not of the film at all, but only of the price in terms of speed that the projecting person is incurring, which would be the same as here, remaining with theta, the angle, in this very simple example, and forgetting this. In the language of field theorists, this is ultraviolet, this is infrared, meaning this is hydrodynamic, this is all the rest. Okay, so now you attempt to do this from the original fermion model. This was done by Maldacena and Stanford, and it's called the Schwarzian energy. This is the cost for the operator to change the speed of projection only. All the rest is gone. But this is for your system. Now it's a scalar theory of reparametrization, and this is gravity at the toyish level we've been. So it gives you all the low-lying state of this strange metal, which is what SYK is, or wants to be at least, and this is the cost. And this is nothing but the hydrodynamics of, in time, of this original model. So you started with fermions, let's say a quantum field theory, but with no coordinates, and you ended, for the low energies, with a very different theory that seems to come out of nowhere, where what you are paying is the cost of projecting at varying speeds your thing. And this is, they tell me, exactly the way in which gravity should arise as emergent from a quantum field theory. mutatis mutandis, because this doesn't have any space or any nothing, but it's a very toy model, but at least this one we understand. Yeah.
Can I make a comment here?
Yes, please.
So actually, in ADS to gravity, you can, because it's two-dimensional anti-de Sitter space, the space is very rigid, except at the boundary, where you indeed have a degree of freedom, which is exactly the same as this reparametration invariance of the boundary. So in fact, the Goldstone mode of gravity and the Goldstone mode of SYK, they are the same.
Okay, marvelous. This is perfect. So apart from the analogy of being the hydrodynamics and classical and all that, which is, it also, this is what Kaplan has said just now, it emerges also if you start from a very peculiar and also rather toyish version of gravity. So now, but I want to insist that this story, as far as I can tell, came from the bound, because this was the first indication of who was guilty in this thriller. Okay, very good. This is given that I have a lot of time, let me say that I told you that in glasses the same thing happens. You can throw the time away. I'm going to be very, very, very quick. But this means that also projecting at varying speeds or changing the speed of projections is very easy. And this is a property of glasses. And let me give you some examples. Glasses, as you approach the critical glass temperature, the liquid does the same evolution, but at a speed that changes with temperature. So again, it's a thing of filming. If you look at how a ruler ages, how its dynamic slowly evolves, it has a certain rule, but if you take the ruler and you do this once a week, you change the speed of the clocks of the ruler, and then you give it to your experimentalist friend, and they measure as if the ruler were younger, thanks simply to the fact that you did some shear to it. Or more recently, we showed that programs that do the evolution of particles in your computer that are super fast, that super increase and speed up your evolution, even orders of magnitude, do exactly that. They do the same evolution, these correlations prove it, just like an operator moving the handle faster. But the film you're passing is the same. The mutual correlations are the same. And finally, a last example is from Tommaso Rizzo, where he calculated how a system goes. You assume that it goes from a deep place to another deep place in a time t, and you calculate how it does so and with what probability, and he got a solution. And now it turns out that if you change this time t, the film is exactly the same, only that the time stretches exactly what it takes to do the same thing in a different time. And this is completely non-trivial, and it was a surprise for everybody. So this to show you that this old idea, this old idea of reparametrization, which was around in glasses, now appears in a very, very shocking and remarkable way in these fermion systems, but also in glasses, it does something useful for you. Yes? Mm. The dynamics is the same except for the fastest motion, meaning the vibrations and motions. So I see it this way. It's as if you have a road and you walk this road or you go in bicycle. The details of the short times, and here what we did is precisely to plot. You have two different correlations, let's say 2K modes, and you plot one against the other. So time is gone. And we do it for the fast dynamics and for the slow dynamics. And the two curves are spot on, one on top of the other. It means that when you put together two correlations, their mutual relation where time is gone is exactly the same in the, in this case, there is 100-fold acceleration. It's the same. No, it's a correlations. And it's a number of correlations. Of course, you don't have to exaggerate too much with the correlation because if they spot us, okay. Okay. Yeah, this is a, well, okay, it's not exactly where an actor is, but it's a plot of the story. Okay, so in glasses this appears also. And if you could write a theory of the reparametrizations, you would be capturing a kind of hydrodynamics of glasses, which would not be a hydrodynamics at all. It would be much closer to the gravity of Maldacena, Shenker, and Stanford. I want to say, or at least there is one person who's a technician of these things, that it's true that both glasses and this fermion system have a reparametrization group, but then this group, which is generated by the Virasoro algebra, in the case of SYK is broken down to a group that is not broken, a subgroup, which is SU11 or SL2, and this is important. For us, it's not. It's just a translation and stretching group. So it's a much more poor group. So the reparametrization for glasses exists, but the residual symmetry is not the same, and this has some importance. So I don't want to, but the fact of having reparametrizations and them being cheap, and this has been worked out and recognized quite a lot, even 20 years ago, by Claudio Chamon, Letizia Cugliandolo, Malcolm Kennett, and Horacio Castillo. Okay, so epilogue. You now have a toy model that gives you an idea of how gravity emerges from quantum field theory. It's of course a metaphor, but it's a metaphor that you can bite, you can really solve it. And you can do a lot of game, you can play with it, and it tells you things that normally you had no theory to do. So you can take two of these SYKs and couple them, and you find that the solution is two coupled replicas, and you interpret this as a wormhole between two black holes. And you can conclude, of course, I insist how metaphorical all this is. But you can do even more surprising things. There are many experiments where people asked, what happens if I throw a spin into a black hole and then where does the information go, etc. You can metaphorically throw a spin into an SYK, which means that you take your spin and couple it to your SYK, and you can follow the information with exquisite detail and solve it completely and beat it to death and see in this very, very simple example how the story goes. Once you've seen it in this metaphoric toy model, you think that you understood how it goes. So this is fantastic. It allows you to not do phenomenology, which sometimes can become very chatty, but you can really do something, which is incredibly nice. Of course, with all due limitations, of course, recognition of the limitation. On the other hand, this thing, coupled to the story of the bound, has revived a lot the field of quantum chaos. And you've seen that in quantum stuff, people are always calculating out of time order correlators, OTOCs. We heard it in the previous talk, and that's natural because this is what you're calculating when you calculate the Lyapunov. And this has been suspected for a long time, but now it's clear, strange metals, so systems that have no quasi-particles but very many low excitations, which are very strange, seem to be related to things that come from high energy. So this is two worlds suddenly talking to one another. So I think that this is all like a kind of big adventure of many elements, some of which are quite elementary. This is not all the horrible difficulties of string theory. So I think that I'm done. Thank you very much.
Time for questions. Just okay, Abhishek.
I have two questions. So one is like, so you said spin systems don't show up chaos, right? So, but even the SYK is a finite dimensional Hilbert. So how is it like this is able to?
What seems to be the case, unless you do very strange things, is that if you have, SYK is zero dimensional, but it has a big Hilbert space in that point. If you have a system that is some dimensionality, but at each point, your dimension is not very high, you have a spin, you have two possibilities, or then there is not enough place to go to have a Lyapunov.
But if I had a mean field spin, like all coupled to all, I mean.
If you have all coupled to all, and
Yeah.
eventually even all coupled to all at each point, and then to all of the next neighbor and so on, then you can have everything.
Then 1D spin chains don't have.
Don't. The quantization instead of Fermi pasta Ulam will definitely have a, because then the space XP at each point is infinite.
The other question was like, is there an analog of this black hole radiation in the SYK?
So this is the coupling of, for example, your SYK to something else, and you start in a state that is inside the lowest ones, you should see it coupling to, for example, a bath, and in this sense, evaporate in the sense that, so also these things have been discussed and to have been, you know, what happens with such and such. So you can play up to a certain point, you have no real space, so it remains a bit at the metaphor level, but you can play with this.
Okay, so if there are no more questions, let's thank Jorge for the nice talk once more.